So first of all, I'm enjoying very much the workshop. Thank you for organizing, or the organizers. It's really nice to be here, to learn, to also understand what's happening in fields I'm not so familiar with in altermagnetism. The superconductivity, it's the first time I hear that in so much depth, which is really nice. So I'll be talking, the original title was Altermagnetic Anomalous Hall Effect Emerging from Electronic Correlations. There are quite a few people that I've been working with on altermagnetism. Especially I want to mention Toshihiro Sato, Sonia Haddad, Cosma Fulga, Mangli Hu. Mangli is there, here, there. And Fahar Assad, Jorge Facio, and Alessandro Stroppa. And I mentioned those names especially because we had an archive preprint this morning, and I'll talk about that, and they are the main protagonists there. Before doing that, I'll just flash this, what kept us busy in the last 2 years on altermagnets. Vladimir, who's also here, worked on curvature-induced magnetization and altermagnets, altermagnetic spin textures together with Helen as well. It was also a pleasure to work with experimentalists in Sweden on while nodes and altermagnets and their Fermi arcs. So lots of stuff going on. But as said, today I'll talk about this archive preprint, which is called ferrospinetic altermagnets from electronic correlations. So it's the first time I give this talk, so if you're not satisfied, then you have to come back another time. Before diving into it, there is a workshop that actually Sungwook Chong is organizing. I'm also there, and Igor Mazin in New Jersey, January 14th to 16th. Workshop on altermagnetism, experimental advances and theory explained to experimentalists. This was not what I put as a title, but a song kind of a.
I think the brainstormer is not there anymore.
Okay, good. So the topic I want. So you're welcome to apply there. It would be a pleasure. Last year it was a very nice workshop. We also had a lot of interaction. It was really also a pleasure. So let's take an insulating system where we know we have negative charges and positive charges, and in a continuum limit, these are continuum distributions. And if I break inversion symmetry, I'll shift the positive and the negative charges with respect to each other. I get a charge displacement and I get a ferroelectric. At least if I can switch it also, people would call it a ferroelectric. Now we asked ourselves, what if we don't replace the positive and negative charge with a spin up and spin down? So we think now we have some kind of continuous distribution of spin up and continuous distribution of spin down, for instance, as in an altermagnet if you look from far away. And now if we break inversion symmetry, can we get a situation where instead of having a plus minus charge polarization, I have a spin up and a spin down and a spin up polarization at the edges. So instead of having a charge displacement, I would have a spin displacement field. And okay, the answer will be yes. And then we thought on how do we call this thing? If this is called a ferroelectric, what is this called? And then we thought ferrospinetic maybe because it's a spin displacement, but if anybody has a better name for it, then or maybe it doesn't need a name, I'm in the market. Okay, so to get
is this in real space that you get spin separation in an
yeah, this so yeah
there,
so
you're showing a real space picture.
This is a real space picture.
Right.
Oh, okay, this is okay. So in German there's this famous Lieder ohne Worte. Yeah, so songs without words. Right. This is physics without math. Right, so this is just hand-waving stuff. And you can just ask yourself, can I have a real space situation where now this polarization is charge compensated, if you want, but spin polarized? Yeah? Okay. In order to do that, we take one step back and talk about a symmetry, chiral symmetry, or electron hole symmetry first. And sometimes, yeah, this is called chiral symmetry or sublattice symmetry. How does it control ferroelectricity? My point will be, if I have this sublattice symmetry, electron hole symmetry, I have no ferroelectricity. So if I make a model that has that symmetry, I can kick it out, and I'm only left with the spins. So I have a switchable electrical polarization when a spatial inversion symmetry is broken. If I have a chiral symmetry, however, which is denoted by this U, the lattice can be divided in two sublattices. I have this unitary transformation, and if it anti-commutes with the Hamiltonian, my single particle spectrum is energy or particle hole invariant. And this means that every occupied site has an unoccupied partner, and there's a zero total polarization. Once the chiral symmetry is broken, then this restriction is lifted, and that allows for an asymmetric electronic occupation between the sublattices, which can give you an electric polarization. So the simplest example, a wonderful example, is Rice and Millie model. So this is one dimension. I have an alternating one-dimensional system where I have two sublattices. On the one sublattice, I can have a potential plus V minus V, and there is also a dimerization going on. So T plus delta T on one bond, and on the next bond it's T minus delta T. This is my Hamiltonian. If I have chiral symmetry, sublattice symmetry, then this I can only have if V is equal to 0. I can have a finite dimerization, but if V is 0, then there is a 0 polarization because of that symmetry. If it's absent, so I have both a delta T and a potential, then I can get a finite polarization. And maybe some of you use this in class to teach about the Thouless pump. And you can calculate this electric polarization as an integral over the barrier connection in this system. Right? Altermagnetism, we know, fully compensated antiferromagnet, broken time reversal, lack of time reversal times translation or inversion times translation. So we do not have a Kramers or pseudo-Kramers degeneracy. The spin split bands and a different symmetry operation connects the two magnetic sublattices, which enforces the spin compensation.
Quick question. So I also teach this in my class. And
Wait.
oh, sorry. And even with the chiral symmetry, you get polarization, which is quantized. No, that's just an SSH model, right? Or am I misremembering?
In the SSH model, you don't get a polarization. You will get the charge quantization. Well, from the Thouless pump, you go from SSH to SSH, and you pump the charge, which is E. Mm-hmm. So you do this pumping, but you go from inversion symmetric to inversion symmetric state. With
if you do this polarization, you get the charge minus E over 2 at one end and plus E over 2 at the other end.
Yeah.
Right.
Yeah, that's what I teach.
Okay.
Right. Now, on the other hand, if you have both dimerization and a side potential as you have there, then you are breaking all of the mirror symmetries. And then instead of going from, then you could have two different charges adding up to 0.
Right.
In that case. Okay, and then it's not half quantized, or then you could have other values.
Okay.
That's in your case. Here.
Okay. So, So for a finite system, then of course the symmetry is different. Okay. Point taken. Now we came up with a model that has chiral symmetry. And it's a checkerboard model or an inverse leap model, if you want, and a variation on that. So it has a square lattice. There are the diagonal hoppings as well, but we put an extra side on that diagonal. Why? Because we want to do Monte Carlo in the end, and we want to stabilize an antiferromagnetic state, a non-frustrated. If we can do Monte Carlo on a non-frustrated system, the Monte Carlo people, which is Facher and Toshihiro, you don't have a sign problem. So we have an unfrustrated Hubbard model here, where you can imagine that if you have a spin up sitting here, and a spin down there, and a spin up there, then this is an altermagnet.
Sorry, C and D are two different atoms?
Yeah, C and D are two different atoms. So one is...
More than one side.
Yeah, so you can think one goes over from A to A here, you go via C. From B to B here, you go via D. And C and D are not connected, let's say. You can make arbitrarily more complicated, but this is the simplest model without the sign problem. So now it also allows for a dimerization, and now the thick lines are T plus delta T, the thin lines are T minus delta T, and we have this dimerization in one direction and also along the other direction. Yeah. So which symmetries did we break? Lattice inversion. We broke glide along the direction x plus y, so that is this direction. The Hamiltonian has time reversal, right? And it has a glide along x minus y, this direction. And because, okay, I was talking about chiral symmetry, now you have to work a little bit more to define this operator U because it's an interacting system, but you can define a many-body chiral symmetry in the following form. It's there. Right. So what we will do is switch on U, and then the system will break spontaneously time reversal. So the U term, as I said, so we are at half filling. The U term promotes long-range antiferromagnetic order, so it breaks PT symmetry or inversion times time reversal. However, the glide along x minus y times time reversal is unbroken, and this defines an altermagnetic state. So that symmetry enforces the total magnetization being 0. But still we have this many-body chiral symmetry, and that forbids electronic polarization. Okay, now we're gonna, the idea is to do Monte Carlo. It's auxiliary field quantum Monte Carlo on this system. This is Facher Assad and Toshihiro Sato, who are the experts. I'm just repeating what they tell me, that you use a torus with the 4 times L squared sides. L can be the order of 10, so it's like 400 sides or so. One looks at observables, which is the spin, the spin-spin expectation value. That's here, and it's interesting that or useful to define a correlation ratio. Which is the quantity expressed here. The point is that if the system orders, then the correlation ratio here goes to 1. If the system disorders for L to infinity, this correlation ratio goes to 0. So if this correlation ratio does not depend on the length of the system, then you are at the critical point. Okay. So this is how this Monte Carlo works. We have now U, and we look at this correlation ratio, and one sees that this correlation ratio is finite. This is for L equal 4. Now you make the system larger and larger, and the correlation ratio goes to 1. So you really start to order, the system starts to order as an antiferromagnet. Yeah. So for L to infinity, this would extrapolate to 1 for any value of U. This is for the system that does not have this dimerization. For the system that does have the dimerization, it's a bit more subtle. So if as before, if the dimerization is small, you have long-range order. So the correlation ratio increases upon increasing a number of sites. But if the dimerization is larger, then the correlation ratio decreases if the system becomes larger, and actually you go to another state, which is a valence bond solid. But we'll stay comfortably inside this long-range ordered situation. So altermagnetic ordering persists also when the inversion symmetry is broken. So now what will happen in this system? And I'll just give you the picture, the rough picture before. We will see for a finite system that there will be a spin accumulation on the left and on the right if I break this dimerization, if I introduce this dimerization. And depending on the size of the dimerization, the spin polarization will be down up or up down. Okay? So here are the results. You can calculate now, this is the finite strip, and we sum over the spins along one line, and we label the lines by this index I, or I2. And here is the, so as a function of I2, the total spin along that line. And the spin will be alternating here. So in principle, if this would be an antiferromagnet, let's say compensated antiferromagnet, this should be 0. And you see that actually it's not. Well, for the undimerized system, the spin in each line is 0. But if you have a dimerization, then, and the dimerization is positive, then there is a positive magnetization, net positive magnetization on this side, and a net negative magnetization on the other side. If the delta T changes sign, it's the opposite. So here, now as a function, we can calculate in the system the total charge polarization. This is a finite system, so I can calculate just R times N, if you want. So the dipole moment of this system. So the dipole moment of the system is 0. It has to be by symmetry, but say, okay, what we call the spin displacement or the spin polarization. You have to be careful because all the spin words are already taken by, so that's why spinetic. So that was not taken yet. So this spin displacement field causes or is finite and scales linearly with delta T, right? So now we do.
Symmetry is broken now, right?
Sorry.
Symmetry is broken now, right?
Inversion is broken. I didn't hear.
Finite moment. It's not. Are you saying there's finite moment now?
There is finite moments.
Okay. So time reversal symmetry is gone now.
Time reversal symmetry was always gone. Okay, in the long-range ordered state. Sorry?
No,
It's not compensated anymore, right?
It is compensated.
it's compensated by order. It's spontaneously. Okay.
So yeah, so my Hamiltonian is time reversal invariant. I crank up the U. It breaks spontaneously time reversal symmetry. The total moment is 0. This thing develops this spin polarization, which is not a spin polarization because one side of this is up and the other side is down. So the total magnetization, if you want, is still 0. Does that answer the question?
Yeah, I think so. I'll come back.
It's
later.
magnetic. It's spontaneously ordered.
Yeah. Okay, now we do the other direction. So I had a direction I called I2. I had the other direction we called I1, and nothing is going on there. You can see that as a function of this dimerization parameter, the spin displacement field is 0, as is the charge displacement field, which is because of the symmetry. So under the altermagnetic symmetry, which is this glide, includes this glide, the spin polarization, spin displacement is forbidden along x minus y because it's odd, and along the other direction, the orthogonal direction, it's even and therefore allowed. and that determines the direction of that polarization. So now this was all with this, artificial, or in some sense artificial particle hole symmetry. No material is particle hole symmetric. Otherwise, we would live without a vacuum, and we are living with the vacuum. So at some energy scale, the particle hole symmetry needs to be broken in the real system. And we can do that in our Hamiltonian by introducing this term, which differentiates between the A, B, and the C, D sides. So the ones that were in the middle of a square, they get a different potential than the ones that are on the corners of a square. So the particle hole symmetry is broken, but the altermagnetic symmetry you can show is still there. So now if I break particle hole symmetry, in general, I would also expect that this charge polarization would show up and be finite. Why not? Because I have broken inversion. And exactly that's what happened. So these are the two directions. This is this x minus y direction. This is the x plus y direction. At the x plus y direction, you see there is, as before, this charge, the spin displacement field. It's here, but there is no charge displacement. And on the orthogonal direction, there is no spin displacement, as I've shown you before. But so the spin displacement is 0, but there is the charge displacement. So because of the altermagnetic symmetry, you can also understand why this charge appears. It's kind of the spin splitting, right? We are used to that these things are orthogonal. So in the altermagnet, where the particle hole symmetry is broken now, I have an electric displacement along this direction, and along the other direction, I have this spin displacement field. Okay. Now you could say, well, that's a very interesting model that you cooked up. It's not so minimal, so should we really worry about that? Mang Li did a calculation, and we found a material with Alessandro. So this is completely allowed in nature, so it should show up somewhere, right? So this is a manganese-based metal organic framework. Actually, Nobel Prize for metal organic frameworks. Yeah, so who knew? It's an altermagnet. It has this glide times time reversal symmetry. And it develops a charge polarization and a spin displacement as well. And you can just get it from your VASP calculation. It's just there. I mean, you could have done this 10 years ago. And you would, because the two spin sectors are decoupled, you looked at the the displacement field of one spin sector and the displacement of the other spin sector, and here you go, you add them and you subtract them, right? And so there is the spin displacement is along this B direction, and the finite charge displacement is along the C direction. Are decoupled? Well, it would be cool, right? If you can say, now I have a charge displacement and the spin displacement. If I switch the charge displacement, do I also switch the spin displacement? And in principle, that is possible, although we didn't look at a specific path for this. So if there is a path is another question, but in principle, it's possible that you change the charge polarization from, let's say, the charge displacement from positive to negative, and you'll see that at the same time the spin displacement will also change the sign. So that means you will get some spin accumulation at the surface, which hopefully an experimental colleague and friend, or not even colleague, can measure. I don't care. So the summary is microscopic model where we have switchable ferrospinatic polarization in ultramagnetic insulators driven by electronic correlation. There is a symmetry locking. The ultramagnetic symmetry locks the polar spin axis, and the chiral symmetry forbids an electronic polarization. That was our first case. And then if you break the chiral symmetry, both sectors are there. We have ferroelectric polarization and ferrospinetic polarization, and we have this material that at least in the computer shows this effect. Now I can stop or I can continue with the anomalous Hall effect.
You had lots of questions, so I think you can go on a little bit. Yes.
Okay, maybe another question. Yeah, maybe.
15 minutes has finished.
Yeah, can you, I mean, maybe I'm having the wrong angle on this, but I'm confused by the, this like spin polarization, because I mean, with the symmetries that you described first, you should be in class D3, and in 2D, you only have a Z2 classification, so that the best you should be able to get is a spin Hall type effect, but that would, you know, then spin up and down at each edge would be the same, and this is not what it looks like, right? And then if you break that, then you should up in the chiral unitary case, and this doesn't have any topology, right? So like
So let's don't get sidetracked by this edge thing. So this edge that I showed is not because this edge state, they're not states, or this edge magnetization is not related to topology. These are not topological states. These are very boring normal states, like if you would have in a ferroelectric where you move charge to one direction, this charge accumulates at the surface there in some kind of state, which is not, in general, not a topological state. Maybe in SSH.
okay, but I mean, it's still usually related to Berry phases, right?
Yeah, so this Berry phase that I introduced is the way to calculate that polarization from a microscopic model to without having to go to this extended finite system. So I can have a periodic system, and there this Berry phase calculations are a tool, a wonderful tool developed by Resta, by Vanderbilt, to calculate this polarization. But it doesn't mean, just like a normal ferroelectric is not topological, this thing is also not topological.
It's not quantized.
It's not quantized.
It's arbitrary, right? So it's not topological.
True, but I mean, for example, in the D3 class, it's actually a statement about each individual Berry phase that it must be, you know, time reversal invariant, even though, I mean, you could apply this also to metals where you also don't have quantized response. But I mean, I'm willing to believe that if it comes from something else. I was confused because you brought up the Berry connection in the beginning.
Yeah, but it is really there. And it can be confusing because I also said Thouless pump, and Thouless pump has something to do with quantization. But I try to help you and not confuse you. But
okay. Didn't work, but I will ask later.
Another question there.
Hi, yes. I had a question about the model. So if I understood correctly, of your 4 sublattices, 2 of them are not connected to the other 2 in any way by symmetry, right? So is it the dimerization that sets the symmetry that the sign, I think you had it on slide 14 or 12? Oh no, yeah, it's here. That the sign of M and M prime is, that's the dimerization that does that.
yeah, so actually yeah, correct. So in general, the spin on C and D are related to it, are opposite and equal, but not so, and for A and B, but not so for AB compared to C and D.
And so you kind of have like 2 altermagnets together, right? Your AB sublattice and your CD sublattice, sort of. What do they necessarily have the same nodal planes in the same places?
Okay, that's a question I didn't think about.
Okay.
So it should be a D wave Altermagnet.
Yeah.
And a simple thing to do, I mean, we did Monte Carlo because that's something that my colleagues do very well, but you could do a mean field calculation. And even in the mean field calculation, you would put in these magnetizations by hand or self-consistently, you would break that symmetry, you would get the same effects that I talked about before. And there it should be very obvious that it is a D-wave altermagnet by looking at how the bands are. Right? We didn't do that, but yeah.
And then finally, sorry if I may, a question about the realization in the real material. Do you there also have 4 different manganese sublattices, or is it less complex in the real material?
Manglish says no, not 4.
Okay. Yes. Okay, thanks.
I have a couple of questions myself, if I don't mind. So the first one is there is a famous example of a material that has spin accumulation at the interface, and this is Cr2O3, which is definitely not an altermagnet. And their inversion symmetry is broken at the interface. So that's one.
It's a magnetoelectric system.
Magnetoelectric
I did not imply that this requires altermagnetic symmetry.
Okay.
I implied if these are orthogonal, it is realized in an altermagnet.
Okay, another kind of related question. So what's the analog, if there is one, of the polarization density at the unit cell level? Because one might not think about the modern theory of polarization, but in the naive way, you have some atoms moving up, some atoms moving down, different charges, and you get a polarization. What's the equivalent here? Are the two
I don't have the definite answer to that, but from the calculation of Mangli, you get the electron, you get the charge density that has been moved of certain spin. So the simplest thing would be to say, now this is mu Bohr. Assuming a G factor of 1, let's say, or 2. But does that you see?
Yeah, it's like a displacement of spin density.
Yeah, it's
almost like polar. But spin.
But so if there is the first experiment, let's think about that deeper. That's a good, I don't know.
Yeah, this is a very interesting effect that you are seeing here. I wanted to know a little bit about orders of magnitude, since you reach the end that you presented the material. So how big are these, in fact, this effect here? So are we talking about numbers that you should really measure, or it will remain a theoretical problem?
Yeah, so I have 2 answers. So look at the charge polarization, which is 1.5 microcoulomb per unit. These are measurable quantities. Why are these measurable? Because charge is, one has experiments that are extremely sensitive to charge. So look at this spin displacement. It's a factor of 10 larger, assuming that we have something like 1 Bohr magneton per. But now, can you measure? So the electrons are there, let's say, or the spins are there. There's a lot of them. And can you measure that? And I would imagine that, knowing that Faraday rotations, so surface Faraday rotations, they're exceedingly sensitive. So that might be the way to go. Then the next question is, if it is useful, it's probably also you need another.
I'm not going there.
Yeah.
I just wanted the order of magnitude.
So it is not, I would say it's not forbiddingly small by these calculations.
Other questions?
So you're making an analogy with electric polarization, but in that case, we have a macroscopic Maxwell equation that connects the bulk polarization, which can be defined with the surface charge density. Is there something like that in the?
It's a good question. We are working on that. So Vladimir, where's Vladimir? Yeah, we discussed this thing. So, if I have 2 plates, right? there's an electric field between those plates, two charged plates. Now I have a spin polarized plate here and spin polarized plate here. What is the interaction between those two infinitely? Oh, that's a question for the audience. Let's see. So I have a spin polarized plane here. A spin polarized plane here. What is but on long distance, what is the interaction between them? Is it attractive, repulsive? Any feelings? So actually it's zero. It's zero. So okay, I think you intuitively go there. So it's zero. Yeah. So it's very different because of the magnetization. If I have an infinite plane that is magnetized, I can ask what is the magnetic field on top of it, and at any location, and counterintuitively it's zero. Yeah. So that's what happens here, of course. So that opened up a whole new, series of things to think about.
Okay, I think we can. No other questions on this. We can move on.
Let's stop here, right? Or you really want to? And the other talk is already I gave some. You're interested in the second part?
Okay,
You
let's
just,
go on. I don't know how much you need.
so I can do 5.5 minutes. So anomalous Hall effect, and we know that it can exist in an altermagnet by symmetry. And the question we asked ourselves, is there a lattice model where you can see this anomalous Hall effect in an altermagnet? I mean, I believe the DFT calculations and they're right, but let's do a model. So if we need some Berry curvature because we are talking about anomalous Hall effect. And we know that we can take a Haldane's model, right? And then we know that it breaks time reversal, it has no spin, and it's a Chern insulator. So that has a bunch of Berry curvature that we would like to use for our purposes. So what should we do? Well, we figured out that with topology we're not going to make it, so not Haldane, but take the model that Marcel proposed in 2018, which is a modified Haldane model where these fluxes on one sublattice go the other direction. Yeah, so Haldane is, let's say, if I look in the middle, all the fluxes like this, and in the modified Haldane, on this triangle is still going there, but the other triangle is going like this. So this is also time reversal broken. But we decided we want to restore time reversal symmetry, and we did this by spin doubling. So to remind you, if I take the Haldane's model, I do spin doubling, I get Kane Millie, and I get a C2 topological insulator. Now we take Marcel's model, we do a spin doubling of this modified Haldane model, we get a modified Kane Millie model, and I'll show you if I also introduce magnetic ordering on this modified Kane Millie model, I get an altermagnet with an anomalous Hall effect. Okay, so here is this non-interacting modified Kane Millie model. This part is the hopping. This part codes for these fluxes in the system, and this is the band structure. So you see there's the red and the blue, so there's a splitting of the bands. So this Hamiltonian breaks inversion, but conserves time reversal still, because we have no magnetism here. We made the time reversal symmetric. So now I'm gonna introduce magnetism in the crudest way possible, saying that SZI minus SZJ, where I and J are nearest neighbors, squared is my interaction term. So I have a huge Ising interaction between nearest neighboring sites. Actually, also I have the SZI squared terms, which act like a Hubbard U term, a local term. If I do mean field, that would be the easiest thing to do. Taking this into account, I would see that there is a gap opening. Obviously, it's like the sublattice gap. And the interesting part is this one. The point of the whole story is this one. Let's look at the Berry curvatures. So the Berry curvature for this spin up, so this blue band is positive. The Berry curvature for this red spin down band is also positive here. And this is not a topological insulator, so there's no net Berry curvature going on here. So the total Berry curvature is 0 and it's compensated by these bands down here. So now you already see this would be a anomalous whole metal if I put my Fermi level here. Yeah? So that's the point of the story. But the main question is this an altermagnet? So you have to, maybe the system does not like at all this ordering, it starts to do something different. And does this scenario hold in the many-body system? And yes and yes, and I can talk about it a long time. And this brings me to my conclusion, that the altermagnetic anomalous Hall effect emerges from electronic correlations in the interacting modified Kane-Millet model. The sublattice magnetization defines the direction, but we already knew this, that the Néel pseudo factor determines the sign of the anomalous Hall effect. Thank you.
Okay, any questions on this part?
I want to comment on this. Long time ago, motivated by the speculation by Chandra Varma of spontaneous breaking of time reversal in the cuprates, where it doesn't really happen. Okay, let me clarify that. We looked with a former student of mine, Kai Sun, who you may not know, we know him. We looked for how to understand why it fails and what can produce something where it doesn't fail. Okay, so we looked at lattice models, but then we looked at simple models of Fermi surfaces with Chern, sorry, not Chern, with no Chern numbers, they didn't have Chern numbers, but with Berry phases. And there is an analog of what happens with the Altermagnet in that sense. Imagine you have two Fermi surfaces which are concentric, and which is a simple case. So they are slightly split. We looked at the spinless model, okay, for simplicity. And we looked at the case where this state spontaneously generates an inter-band, if you wish, or inter-Fermi surface Berry connection that winds around the Fermi surface. When that happens, that's a zero field, that system has a zero field Hall effect, which is not quantized, because it's a metal, so it cannot be quantized, okay? But it breaks time reverse, so it's similar probably what happens when you put your Fermi energy down there, okay, in a sense. So it breaks spontaneously time reversal in that case, okay? And it will have essentially an anomalous Hall effect spontaneously, not by breaking time reversal explicitly, but as an ordered state, if you wish. It's probably close. Well, we didn't put in. You could imagine that one band will be up and the other one is down, if you wish. You could have used, but then you break the SU2 symmetry of the spins in that case. We just took two spinless states.
So I put flavor, you could say I have sublattice A, sublattice B. The flavors I put spin up and spin down. You can take two flavors and you'll be ready.
The game we played.
Yeah.
But it's an example where that can happen. But you cannot do it with a single Fermi surface. Okay.
Thank you. My question is, so in the system at the beginning that you showed for this second part, how many nodal planes do you have? How many nodal planes? What is the winding of the spin polarization? You show alternating spin splitting between K and K prime, but if I could look at this, I don't know how many. Why do you call it altermagnet?
I have an answer that. So when I say this is an altermagnet, you could say, well, okay, then switch off spin-orbit coupling and show me. If I switch off spin-orbit coupling, I lose all my fluxes, I get graphene. which is not by no also magnetic ordering on graphene is not an altermagnet. So I did a mind trick, which you didn't buy, which is good. Yeah. So I put the altermagnet in the end because I know I need anomalous Hall effect. I need spin-orbit coupling. Here's my spin-orbit coupling. Wait. Here's my spin-orbit coupling already on the one particle level, and then later I put in the magnetism, or well, nature does it for me by this term. So I have both the antiferromagnetism and the spin-orbit coupling, and I get an anomalous Hall effect. Now the question is, what type of altermagnet would you have? Is this D or F? Is it even odd? Okay, that's a difficult question to answer because I have nothing without spin-orbit coupling. I have no altermagnet without spin-orbit.
But what does red and blue represent here? A spin up, a spin down, right? So you do have an alternating spin polarization that, if I understood correctly, is F wave. Yes. Right? So you have an odd wave system, and then when you add magnetism, you are breaking time reversal symmetry, but the spin polarization, the winding is not really changing, right? So I'm not saying the system is super interesting, but I just don't understand the nomenclature.
Yeah. So I would. Okay, it's about words. It's, I mean, physics. We do not agree. Yeah. So, but the question is, do we want to? We do agree on the physics, sorry, and on the word. So everything you said is right, and also I think what I said was also correct.
More important than words.
Yeah. So
it's just to understand.
So let's say, how do we classify an altermagnet in the presence of spin-orbit coupling? Yeah, and I do not know the answer to that. So that's why I would not say call this F wave. Maybe Libor has the answer to that.
I have the answer, but I want to still follow on Rodrigo. And so I'm looking into the supplementary information of your paper. And the answer is that for positive and negative wave vector, you have opposite spin polarization. So how this has such a band structure prevents anomalous Hall effect, doesn't it? No, but why no? Yes. The answer is yes. So why no? Why no?
It's the okay. I have two things. I have one electron stuff. My one electron stuff has spin-orbit coupling in it. It has no anomalous Hall effect. Correct.
No, I understand all of that, but I'm looking here at this band structure, yeah? And this band structure has time reversal symmetry in momentum space. So for opposite wave vector, I have opposite spin.
No. So okay, we should put K
even
and
the plus
K prime, and I think the spins at.
It's magnetic now, but is spin flip times what rotation is a symmetry still? Is it odd? I mean, that's inversion.
Okay.
There can be no anomalous Hall.
Yeah, exactly.
So. Okay, okay. You'll have to excuse me, and I'll get back to you after the break.
But you understand what I'm asking about? No, Roser.
So,
Roser, we have.
The question is irrelevant, but for his results, it's relevant. For the question is irrelevant.
No, that's not true.
That's the problem. That would be zero no matter what.
Exactly. You see. So it's very relevant question. On contrary.
that is correct. That is a correct statement. But okay, somehow it works differently here. But I'll tell you after the break.
It's magnetic now, right? Can you calculate the Hall conductance?
Sorry?
Can you calculate the Hall conductance?
Yeah, that's what I show.
And if it is not zero, then it breaks the reversal.
Yeah. Yeah. So okay,
Eduardo,
let's. Can I calculate the Hall conductance?
Then the integral of it must vanish.
So this is the Hall conductance. Okay.
So if electronic structure preserves time reversal symmetry, the whole.
But there is no. He's done some mean field.
Jeroen, you know the answer.
No, I'm going to guess the answer. There is no. So the spin-orbit coupling is not the K-Meili spin-orbit coupling, right? There was a twist of the story. It's not allowed. It's not allowed by the symmetries of graphene. The spin-orbit coupling.
It is not allowed by the symmetries of graphene, okay? So that was going to be my question, is can one imagine a system in which that spin-orbit coupling is compatible with the symmetries? So 6-fold rotation is broken? It's already broken, yes. Okay. It's already broken. There, right? Yeah, by the spin-orbit coupling.
He's doing a Haldane system.
No, it's not, no. It's a...
That's right. 6-fold symmetry is broken.
It's already broken because
that's
it's not
right.
it's not
your model does that.
It's not K-Melee.
Yeah. That's right.
It's a different spin-orbit coupling, not allowed by the symmetries of just the honeycomb lattice. Okay, that's where sort of the twist is. That's where what enables all of this. Because that's why you yeah okay.
Sorry, but the Brillo don't sketch what very 6-fold rotation is.
Yeah.
But it's not about the 6-fold symmetry, it's about the time reversal symmetry.
That's broken, it's magnetic.
It's broken. Yeah.
Sorry, but there are many magnetic systems which do have anomalous overlap. This argument doesn't tell anything.
But it tells you.
No, but what other symmetry would prevent it in this case?
Time reversal symmetry.
Well, that's not present.
Well,
Well,
okay, but time reversal times any. I mean, if the
If
two
that were
magnetic
present,
sublattices
yes.
are related by some symmetry, right? Let's say 6-fold rotation.
Then 6-fold rotation times anti-unitary spin flip is a symmetry of the system. Let's assume it was. And then, okay, so 6-fold, yeah, must be broken then. But
look here, look into supplementary information.
yeah.
So I
Guessing based on what I just heard.
okay. So if you doubt the thing, then we can also go to the low energy model, and I can explain you in detail how we get it in the continuum if it's there. Believe me, it's there. Oh, okay. It's not on the slides.
But I don't understand from the argument why.
I'll explain you after the break. I need some time
Thank
to
you.
be sure that everything I say is correct. At the moment, I do not.